Well, happy to have the opportunity to speak about this amazing sounding rocket mission. I am Aaron, I'm the PI, and I'm happy to work with these listed co-Is. In-house, I see Rob and Glenn right here. So ECHOES is the sounding rocket to reveal the origin of equatorial 150-kilometer radar echoes, which you'll learn all about here. And the status is it's selectable. So this is one of the missions that was selected, but unfortunately has no funding currently because the Peru campaign is not currently funded. So we can all hope that the funding gods smile upon us and give us funding at some point. So do I hit the green arrow? Okay. Okay. So a little overview before I get into the echoes, and Rob just went over this pretty well, so I don't really have to go into detail, but the Peru sounding rocket campaign is an opportunity to explore this largely unexplored region in situ, at least, near the magnetic equator, where all these interesting phenomena occur. And so here's a full day of Hicamarca backscatter echoes, like Rob showed, showing a number of phenomena that exist. And I'm focused on this daily occurrence called 150-kilometer echoes. And so the dynamics of this region are important, for a lot of reasons, related to space weather, and one of them is communication and navigation disruptions. So unfortunately, there are so few in situ measurements in this region. Rob gave the slide of the past sounding rocket campaigns, and they're all sort of the distant past at this point. We have much better instrumentation available for rockets nowadays, and so let's go. Let's find funding and go. It's that easy. So what are the echoes? And so they're a daily feature observed at the radar. And I have a quote here from a paper, and I can't find the quote now. And they're one of the most enduring mysteries of ionospheric physics. And I think the quote is in reference to the fact that we've observed these since the early 60s, but until very recently, we've really had no idea what causes them. And so they are, this is a daily occurrence, and this is what the general shape looks like. You have this pearl necklace shape where the echoes, the backscatter is strongest at low altitudes, around 130 kilometers at noon, and then at higher altitudes at dawn and dusk. And this profile actually matches fairly nicely the expected profile of photoelectrons, which is shown here from a simulation below. And so only recently, in fact in 2016, Oppenheim and DeMont came up with this idea that these are actually driven by photoelectrons in the 20 eV or so range that drives upper hybrid waves, which cascade down into these echoes, which are observed in the backscatter. And so for decades, we've had no idea. Now we have this plausible hypothesis, which actually nicely explains some of the basic characteristics of these echoes, but it's largely untested. So, and why do we care? Well, the echoes are essentially omnipresent in this decades-long data set of Hicamarca observations. And really there's a lot of features of these echoes, the overall pattern, the layering, the tens of minutes to tens of minutes modulations, and these really can be a fantastic proxy for physics, ion and plasma and neutral physics happening in this at these altitudes and to different latitudes, since the magnetic field lines are horizontal at this point, if we can understand them. And so if we can understand these, then we have this amazing data set to reinterpret. So here, 9 consecutive days of echoes, just to give you some sense of the daily variability. And you can see, you always see this necklace shape, that's always there. The peak power, the peak backscatter can change as a function of local time, but it's typically around noon. And so the main morphology is this necklace shape. And the reason we think that minimizes at noon is because EUV photons go through less atmosphere at noon than they do at different local times, and so they get down to lower altitudes. There's also the pearls. If you look at the zoomed in plot or the high power mode plot in the bottom left, you see there's all sorts of interesting substructure for these echoes. And some of this might be related to gravity waves or other dynamics going on. There's very clear altitude boundaries. So these are really never seen below 130 kilometers. That might be because collisions are very dominant then at those altitudes, but maybe not. Maybe it could be a lack of free energy. And there's upper cutoff, usually around 170, 180 kilometers. And so the final feature I'll point out is the layering, and including the forbidden zones where you don't actually see any echoes. And so there are some clues as to what's happening here. So this is a diagram Glenn and I came up with following the theory of this. This is from the proposal. It really comes from a combination of the theory and PIC simulations that suggests that these photoelectrons are driving upper hybrid waves that are somehow cascading down to ion acoustic waves, the foam. So, which is interesting because the upper hybrid waves are on centimeter scales and ion acoustic waves, centimeter scales in megahertz and electron waves, and they're cascading down somehow to meter scale ion acoustic waves at kilohertz frequencies. And so the idea here, right to left, is that photoelectrons in a very narrow band of energies are created. They grow upper hybrid waves via cyclotron Landau resonance. There's also thermal electrons around which can provide damping. So some combination of growth and damping gives you the upper hybrid waves that are observed. And then those non-linearly cascade and cross-scale couple into the ion acoustic foam, which is at meter scale. And Hickamarka at 50 megahertz signals are really good at backscattering off of this 3-meter foam. And so even if the foam in situ is not large amplitude, these ion acoustic waves, they provide a very strong backscatter. And so echoes will come in because echoes will test every piece of this picture to verify or reject this hypothesis. And we can finally do this because the final piece of the puzzle is in place, and that is the, Glenn, and I don't know if you have it on you. You always carry it, except for, I'm joking, he doesn't always carry it, but I was hoping you'd have it on you. The photoelectron spectrometer, which Glenn flew on the amazing Endurance mission, which there's a Nature paper now, where that team has measured the ambipolar electric field with this instrument. It's a spectrometer that focuses on a very narrow range of energies, in this case from about 20 to 30 eV, with very, very high delta E over E, 0.5% I think it is, as compared to about 15% for a normal spectrometer. And so we can test this entire hypothesis, start to finish. We'll measure all the variables, we'll correlate the wave activities, and we'll calculate the growth and damping to see if this all holds together or not. And if not, we'll have a lot of data for a new hypothesis. So here's a cartoon of the payload and the instrumentation. The star of the show is the photoelectron spectrometer that I just talked about. And it's the only instrument that can measure these photoelectrons resolved. And then, of course, the fields package, which consists of electric field double probes and a magnetometer, and high HF receiver, also at Goddard, and then a Langmuir probe from Embry-Riddle. And, of course, Hickamarka observations, and then theory and modeling by William Longley and Mears Oppenheim. So I guess further motivating the need for this high-resolution spectrometer, this is a plot of the simulated photo peaks that we expect to see from over the course of this flight. And so the second panel are the lower energy photoelectrons there's this distinctive N2 absorption feature. And these peaks were all seen in the Endurance flight. I think they're just much weaker than we'll see them much stronger here. But if you look from 16 to 26 eV, there's a number of photo peaks, and this is from ionized nitrogen states, I believe. And so we'll actually, with the photoelectron spectrometer, be able to resolve all these peaks. And so once we know that, once we know properties of the plasma, we can calculate the growth conditions, which is really the standard cyclotron resonance condition here, and also the damping. So the thermal background of electrons will damp the waves. In fact, they have almost no parallel to the magnetic field velocity, so the resonance condition just indicates that you would see damping at integer values of the cyclotron frequency, which can explain those narrow band gaps, but we'll measure that. So what we're going to test to see if the growth plus the damping leads to upper hybrid waves. We're going to see if those upper hybrid waves coincide with ion acoustic waves in 2 minutes, thank you. And whether those ion acoustic waves, are giving the reflections that we observe as the backscatter. So we're going to fly 1 to 2 rockets. The way budgets go now, maybe 1 only, but we'd like to fly 2. So a single rocket would be launched northwest out of Punta Lobos range towards the dip equator. And we'd go take measurements below, within, and above this echoes region, probably around noon local time, upwards and up leg and down leg shot. So a second rocket would, aside from the obvious of ensuring mission success, if we have a failure of an instrument or rocket, it would allow us to actually target a different trajectory. So we could, for example, launch at the same local time, but launch at a lower apogee, increase our dwell time within the echoes region, because the spectrometer needs to integrate for some amount of time. And so we could also launch into different conditions. So what are the benefits? The main takeaway is the results from echoes will really allow better utilization of Hickamarca observations. So 20 plus years of really high resolution observations to be reanalyzed. If we understand all the bumps and wiggles and morphology and what that's tied to physics-wise, these really become an amazing proxy for the physics going on at these altitudes. And I'll mention there are other radars at near equatorial latitudes. Hickamarca is the most powerful one. It's the one that sees the echoes the best, but it's not the only radar that does see these echoes. And so have some hope of understanding longitudinal variation near the equator better than we do now. So there can also be additional benefits. We might, so this Pearl minute scale modulation is probably related to gravity waves, which we won't measure, but it could be related to density changes. And so we might get some insight into that. Just the insight into the altitude cutoffs. The lower boundary is probably due to collisions dampening this instability, but we don't really know what the upper boundary is caused by. There's probably ideas, but we don't really know. We'll provide much better data for the PIC simulations, which are not well constrained at all. So, and then just general nonlinear onset of turbulence and its evolution. It's a large scale problem. It's not well understood. And this is the perfect example of an in situ laboratory where you have this cascade from electron scales to ion scales, and we're going to get fantastic data that might provide some insight into this. So I'll just finish, and this is, Rob essentially said this, but it's a Peru call to action. This is really a once in a generation opportunity to go after all these interesting science questions, and with much, much more advanced instrumentation than we've previously had. And Rob had this exact plot in upper right, but the last campaigns are now decades old. And so fingers crossed we get a chance. So that's my talk. Thank you.